All right, we'll be getting started in sort of about a minute or so. Yulia, do you want to turn your camera and microphone back on?
Yes, let me try to do that.
Great.
Hello, everyone.
Yeah, we can definitely hear you. Excellent. And just to check in with Tim. Tim, are you good to go when we get started?
I am indeed, yes.
Okay, all right. Well, we still have some people coming in, but it is 4 o'clock, and we can just do the brief introduction here and buy them an extra minute or two to connect before the talk starts. So let me stop sharing here. And let me start by welcoming everybody back to the SMU Physics Department Speaker Series for Fall 2020. And we are continuing our October series and its theme of probing the unknown. And today, we're going to have a really nice talk looking at a very exciting future facility in the United States for nuclear and particle physics as well. So in a moment, I'll hand things over to Tim Hobbs to introduce our speaker, Dr. Yulia Furletova. But before we get started, just a brief reminder to our audience on Zoom. So the Zoom audience can interact, and to ask a question, because you don't have control over your own mic for this, just go to the chat window, type the word speak into the chat window to indicate that you wish to speak, and we'll interrupt the talk at the next opportunity, like the end of the slide or so forth, and let Yulia know that there's a question from the audience. You have to wait till you're unmuted by one of the moderators, so me or Tim, for instance, because we have control over the mics. So don't start talking right away. We'll let you know when you're unmuted, and then you can go ahead and start asking your question. And then just in general for everybody, a reminder that this event is being recorded and simultaneously live streamed on YouTube. So hello to our audience on the live stream on YouTube, which is non-interactive. All right, so let me hand things over to Tim to introduce today's speaker. So thank you, Tim. It's all yours.
Yeah, excellent. Yeah, and thank you for the welcome, Steve. So we're indeed really pleased to have a friend and colleague of ours, Dr. Yulia Furletova, who will be giving us, I think, a very interesting talk today. Just a little bit of introduction about Yulia. So Yulia did her PhD at Hamburg University in Germany in 2004. The topic of that research was primarily physics beyond the standard model, and in particular, a concentration on leptoquarks. Now, since 1995, Yulia was involved in the Hera B experiment at DAISY in Germany as a graduate student, and also at the Moscow Engineering Physics Institute in Russia. In the past, she's participated in the development, construction, and operation of a transition radiation detector, as well as aging and performance studies of a honeycomb-based outer tracker. In the year 2000, she joined the ZEUS experiment at DAISY, and during that time was responsible for the beam and background monitoring detector at the ZEUS experiment. She also participated in offline reconstruction software development. Yulia served as the run coordinator, the shift leader, and an on-call expert during the ZEUS data-taking period. She then did postdoctoral research at the University of Bonn in Germany, working on the DepFET silicon pixel vertex detectors for ILC and Bell 2 experiments, and then also worked as a staff scientist then at the Yulia Research Center in Germany on the development of a neutron imaging detector. Yulia has over 100 publications in refereed journals, and more recently, Yulia joined the Jefferson Lab in the year 2015 as a staff scientist working in the Electron-Ion Collider Center, the EIC Center, where our group actually has some activities. And currently, Yulia is involved in the EIC detector and the IR, the interaction region designs, and at the moment is really leading a GEM-based TRD R&D project, and Yulia will tell us, I'm sure, a little bit about that. More broadly, she's also just involved in a number of activities related to open charm production, as well as possibilities for testing the electroweak sector in the standard model and searching for BSM physics at the EIC. I'm sure we'll hear some exciting news about all of those things. So with that, I'll turn it over to you, Yulia.
Okay, thank you very much for a nice introduction. Yeah, as you can see that, so I have some background on different topics, but today I am going to focus on charm. Let me start sharing my screen, and please let me know if you can see my slides.
Yes, indeed.
Okay, super.
Excellent.
And I need to remove this part of here. So thank you very much for your nice invitation. So it was really nice to be here and present you what is the current the Electron-Ion Collider activities. In particular, since this topic will be about the gluon, so I will talk about the charm tagging and how we can use the charm tagging for measuring interesting physics at the EIC. So before I jump into this heavy flavor topics, I will introduce you to the current EIC user group activities. And we'll talk about what kind of detector developments we are doing right now and for the EIC, and also some physics motivation for those detectors. Then I will describe you our LDRD project, where we focused on heavy flavor tagging. And I will talk about, what kind of reconstruction we used at to probe large X gluons, and what was the impact on nuclear gluons. And at the end, I will also let you know about the other processes which we actually didn't study at that time at the LDRD, but they have really a lot of potential for the EIC. So let me start with EIC activities. As you can see here, the timeline for the EIC. So it started long ago in 2002, when it was the first time mentioned during the long range planning. And it's, in like a decade after that, the EIC community actually summarized the physics requirements in the white paper. And so it was mentioned also multiple times in different long-range planning grids. And in 2018, we had a National Academy of Science review, where sort of all these physics topics were analyzed and approved. And a year ago, two accelerator proposals were sort of delivered to the Department of Energy. And less than a year ago, so it was January 9, when the DOE decided on a site. And now we know that this facility, so this is really a large scale accelerator facility for the next generation, the next decades of running for the nuclear physics, will be built at the Brookhaven National Lab. So since then, the BNL and the J Lab are working together on the conceptual design report. And also I will mention about the current EIC user group activities related to the so-called yellow book and the physics detector requirements. So about the concept of EIC, as I mentioned, that it will be hosted by the Brookhaven National Lab. So it will be built on existing RIG facility. What does it mean? At RIG, we already have a hadron collider. So we have already a tunnel for the hadrons with all the injecting schemes. What it will bring on top. So we will have also the electron storage ring. So this would allow us to accelerate the electrons from 2.5 to 18 GeV. The hadron energy scale, which in the range of the existing RIG operation, so going from 40 to 275 GeV. We will have really large current, so this will many benches. So the repetition rate will be close to the 10 nanoseconds. That would allow us to keep the high luminosity for the interaction region and have more data. So what is really important that we have the crossing angle that would require some crab cavities installed in the system, and really good instrumentation for the far forward areas. So this is the existing and proposed EIC concept from the existing RIG to the EIC. As you can see, the multiple storage ring and The accelerator rings will be installed there in addition to the existing facilities. And this is how it will look like in a sort of the cross section of the tunnel. Let me first introduce to the interaction region, because, you know, since we are all the experimentalists, so we would like to know how our detector will look like and what kind of available space we have and what, you know, accelerator people actually, you know, prepared for us or saved for us. As you can see from this picture, so the interaction region is really crowded. So we have, but we asked them to keep at least, you know, 9 meters at the, next to the IP, sort of the iron-free zone. So the zone where we do not have any beam elements in this area. So that means we can place our detectors as close as possible to interaction to the beam pipe, and there will be no sort of limitation on acceptance coming from the accelerator. But in reality, as you can see, that the 9 meter is only central detector, so what we call the general purpose detector. But in reality, our detector are stretched, you know, 40 meters in the both direction, because we really need to keep good instrumentation for particles going in at the shallow angles, or like diffractive processes and low Q square. So this is diffractive, I am talking about, or tagging for the far forward region or the low Q square electrons, and I'm going to touch later on today about this. So that means, as you can see, the interaction region is really large. So that means we have to really keep you know, the full integration of our detector with accelerator at the early stage. So we have to really start thinking and planning how we are going to do that, so that we the design, which, you know, of the AC detector, which we are planning to operate in the next decade, would really serve the physics purposes. And we have to also keep in mind that this facility will be operating with different beam energies and with a really high luminosity. So we have to really pay attention that, you know, we really can provide right acceptance for the different beam operations. So let me switch to the user group activity. So currently we have more than 1,000 members. More than 600 experimental physicists, accelerator physicists, theoreticians, and other people from you know, more than 200 institutions all across the world. So what we are currently doing, we are trying to get requirements and link actually requirements from the physics to the detector requirements, and evaluate if this detector can really serve the purpose which is really needed for the EIC. As you can see from this picture, we have a very, very asymmetric collider. So we are planning to, we will have electron coming from one side and ion beam coming from the other side, and the energy will be completely different, and the different parts of the detector will be serving different purposes. For example, and I will come back in the next slide to this. So for example, this area here, which we call the electron-ion cap, the main purpose of this area will be to detect our scattered electrons. So this is the part where most likely our scattered electron will be detected. From the other hand, what we call the hadron end cap, this is the most likely place where all the jets or decay particles sort of will end up, and barrel part, or this of the central detector, of course, this is dual purpose. So this will be designed for the high Q square electrons and for the high PT hadrons. And I'm not showing it here, but of course we will have a lot of particles going along the beam line, and we have to provide very good instrumentation for the far forward hadron direction and for far forward electron direction. And as you can see, so the central detector will be sort of covering the area close to the foci. For those of you who are not familiar with deep inelastic scattering, so this is a really unique facility compared to the, for example, PP collision at the LHC. What is really important here that with this process, we have our scattered electrons, which actually define the kinematics. So once we measure the scattered electrons, we know precisely what x and the q square of this reaction, what was the x and the q square of this reaction. So there's really precise measurements of the, and precise control of the kinematics. So I told you that we are going to have a different q square coverage, and this is what actually defines your resolution. What kind of the resolution you can probe of the particles inside the protons. Also having the ability to change or probe different particles at different x, for the different x would define the different configuration and dynamic inside the proton or ion. So this is really unique facility, and we have to use really advantages of this. So I told you about the kinematics. So let me show you briefly this plot. Here you can see the isolines plotted on the x and the q square plot, and the red curve showing the constant energy for the scattered electron. The colored area here represent barrel, hadron end cap, or electron end cap. And as you can see, the barrel part or the electron end cap part will mostly serve as for the low energy operation, while the high energy of the scattered electrons will be mostly in a barrel or even in a hadron end cap. So this is, and they will touch the area corner space of the large X and the large Q square reactions. Again, here, as you can see, we can define our kinematics just by measuring angle and the energy of the scattered electrons. And this is unique opportunities of the EIC, as I mentioned. And so this is the formula which you can use just for definition or for reconstructing your kinematics. But this method have some disadvantages. First of all, it has linear dependence on the energy of the scattered electrons, and as you can see here, it really cannot go to the cannot be applied for the y beyond 0.1. That means this method will provide excellent resolution, but only for this small band here. So what we do in order to extend for the different for the low y operation, so we can look at the also response of the hadrons. So kinematic of the hadrons is slightly, not slightly, but completely different from the electrons. And again, so the red one are the isolines for the constant energy of the struck quark. And again, as you can see, the farther we go to the large X, the higher the energy of those struck quarks. So I'm talking about this struck quark from the reaction becoming larger and larger. And what is really important here to notice that the resolution of the energy measurements really define the resolution of the X. So as you know, if you measure very precisely your energy of your struck quark, this is what kind of resolution of X. So it's one-to-one comparison. As you can see, all those lines are sort of defining you the X of the reaction. So that means we have to really pay attention during the design of the detector and provide really good measurements for the energy of the quarks or jets. Here are different methods which one could use to improve your resolution in the different areas. As you can see, those methods actually combines the information from the scattered electrons or the scattered or the quark. And for the Jack-Blundell method, as you can see, only hadronic final states are in use, so that and this is the only method which could be used for the charge current reaction, for example. So very briefly about the total acceptance detector. So it's very much close to the general purpose detector, which we used to have in a different colliders like proton, or E plus and minuses. And a few words about the far forward area. So I will not really introduce you to these numbers, but you will see we will have Raman pods, we will have 0-D calorimeters, and we will also have some instrumentation for slightly larger angular coverage in a dipole in front of the interaction, right after the interaction region. So interaction region is here. Also, we are planning to have, and I hope we will have, very good instrumentation for the far forward electron direction, or we call it backward direction, for the low Q square electrons. So this is sort of the photo production regime. Also here, so this is the tigers which we are planning to have, and luminosity detector, which we are going to use for the luminosity measurements of using the Bremsstrahlung photons. So currently in the user group, we have two groups working together. So one is, we call it physics working groups. It's subdivided on different sub-working groups, so like inclusive, semi-inclusive, and exclusive reactions or tagging. So what we are trying to get out of this is sort of a list of the requirements for the detector people, so that they could refer to the physics studies and see what kind of detectors needs to be placed where in order to get the good response and actually make those reaction possible for observation. So another working group is the detector working groups. As you can see, it's also subdivided in different subcategories like tracking, PID, and calorimetry. So those working groups are trying to get actually the detector technologies work together so that they could satisfy the physics requirements, which the previous group sort of setting up. And here on this plot, you can see the upcoming schedule. So we are at this line at the moment. And as you can see, very soon we will have to actually start constructing already this detector and the accelerator. And in FY30, we have to be already close to the operation. So this is really a very interesting time where we could still have to, where we still have a possibilities to change the things. That means we could push and, and make the best out of the best detectors happening for the EIC. And so after, certain decisions, it's actually will not be already way back. But right now we are living in really unique time, so that we can really have possibilities to change. So now let's switch to our projects. So this was the LDRD projects on nuclear gluons at EIC. So list of the participants. Also, I put here the link to our wiki page. So what we try to do actually, so what we try to look with our project, this was the question which we asked, sort of how the densities of of quarks and the gluon, in particular gluons, are changing in sort of in the heavy ion environments. What will be the nuclear modification and corresponding nuclear interactions, and how they actually emerge from the microscopic theory. So, and this is really the next step. So we already more or less know how the single nucleon structure look like, but we need to really go one step further in order to really understand all these nuclear modifications. Let me skip this one. So what I am talking about is, you're probably familiar with this plot, which is sort of showing the nuclear gluon ratio as a function of X. And you can see the distinct, areas, and one is sort of what we called suppression area, or where the EMC effect is happening, and enhancement area, we call it anti-shadowing, and also the shadowing area for the X below 001. And what we are actually trying to understand is really, look at this area at large X and see if we can really get some probe, which sort of will show us how those densities really behave in this area. So, and as you know, we have a lot of really facilities who could really help us to answer these questions. We could look at the Q-square dependence with F2, FL. We could look at the jets on PP collisions. But what is really important, that heavy quarks production really probe this directly, probe those gluons directly. And this is uniqueness of this process. And as I mentioned, that the EIC capabilities will provide really unique possibilities for us. So first of all, this is DIS facility. That means, as I mentioned in my previous slides, we will have control under the kinematics. We know exactly when this reaction and what was the X and the Q square of this reaction. We will have all the variety of the nuclear beams. So this will be first in the world Electron-Ion Collider. So, and we will have various center of mass energies from 20 to actually 140 GeV, so sorry for the mistake. And this would provide really large coverage in the Bjorken X. And high luminosity up to the 10 to the 34, this is where we get access to the rare processes. And of course, next generation of the detectors and the PID detectors. So on this reaction, you see this so-called boson, or what some people called photon gluon fusion. So we called it boson at Hera time because it's also involved the Z exchange. But this is really the unique reaction which would allow you to probe those gluons actually directly. Yeah, and as you can see, if you just look at the so you can see we have two different X in here. So the Bjorken X and gluon X, which is what we call X prime. But as you can see that we are probing those gluons almost locally. So that means there is a slight modification, but this is how for the certain bin of the Bjorken X, this is how the gluon X will look like. But it's almost locally. Of course, we know all the high leading or the next leading order corrections for this process, so everything is under control. Just a reminder that, of course, the EAC will not be the first EP Collider or DIS facility. So we had Hera, and thanks for Hera, because this was really where we learn about all those processes and problems. And just would like to compare that, at Hera, so the Zeus experiment, after the 10 years of operation, we collected half inverse femtobarn. So the half inverse femtobarn during, after the 10 years of operation. Well, at EIC, we are planning to have from 10 to 100 inverse femtobars a year. So this is, you can see that this gap between the data which we are planning to get at the EIC. And so this is again data from here. So what we study is the different F2 charms, and mostly, as you can see here, mostly for the low x, for the x beyond 0.01. What is plotted here is a cross section as a function of the q square for the charm. Actually the D star here. So what we used at that time, we used the HVQDS calculations. And as you can see, this it's showing actually in yellow, it's showing you the that this those predictions which we have from the theory are really very well described the data. And actually, as you can see, there's like 4 orders of magnitude in the q square. So this was a low q square and the high q square. As you can see, very, very good precision. And so this is what we are actually using our calculation also at the EIC for the comparison. So what kind of lessons learned we know from HERA? First of all, at HERA 1, we didn't have the vertex detector and also PID for the hadrons. And we were only able to use these so-called golden channels. Golden channels is called D star plus going to the D0 and slope ion with a decay of D0 to the charged particles, protons and kaons. Why this was the only channels, as you can see. So if you subtract masses of D0 and D star and plot them here, as you can see, you will immediately see the invariant, the mass of the slope ion, so-called. And this is the only process which doesn't really require any vertexing or the PID. So this was really advantage that at least this one we were able to reconstruct. But for the HERA 2, of course, you know, after inserting the vertex detector, it makes the life much easier. So we were able to include all other channels and measure, for example, this the fragmentation functions for the D star, D plus, lambda C, and so on. So now let's look at the prediction for the EIC, especially for the large X. So as you can see on this plot, number of events for the 10 inverse femtobarn as a function of the Bjorken X. What you can see here are the different Q square bins. So the dashed line is a total DIS, so that means the mean bias events. And the solid line is a charm in this area. As you can see, for the large X operation, we are dealing with a very high background coming from the DIS. So this is the, you know, we will have, so charm to the DIS ratio is around like 2 or 3% in this area. So we really have to find a good instrumentation in order to really extract our charm out of the data. Also, let's look at the kinematics a little bit. So since we're talking about large X events, so those are produced, so these CC bar pairs, which we have in the reaction, they are produced almost at the rest. So that means all of the CC bar will be like back to back if we are talking about the low, so what we call the low electron-proton ratio collider. So if the energy of your initial ions compared to the energy of your electrons will be sort of close to 1-to-1. But if we are operating at the high EP ratios, we will see the boost towards the hadron and cup. So that this is what you can see here. Again, so as a function of the rapidity, all your products will tend to boost towards the hadron and cup, and this will make life a little bit more complicated for the reconstruction criteria. So I probably will skip this slide. So this is questions about what we tried to answer during our reconstruction. Let me show you two methods which we used. One is actually based on exclusive reconstruction of the exclusive process or exclusive decay. So we identified only decays which sort of goes into the charged hadrons, as you can see here for the D star, D0 and D plus, going to the pions and the kaons. And again, so if you just look at this table on the branching ration, you immediately see that even if we will have really 100% efficiency for all those channels, maximum we can get efficiencies close to the 10%. At Hera, with no PID and no vertexing, we had approximately 1% out of this table. So that means we, so even it's really interesting, but we need to think about this. What at the low, at EIC, all the energies, so compared to the Hera, the energies will be really much lower. So as you can see, this golden reaction, those slow pions will be really, really slow. So that meaning that they barely will touch the few layers of the vertex detector, and will make the so this will be the main sources of the reconstruction and efficiency. So because we will lose particles which are below 100 MeV. And the problem is that we cannot really place the vertex detector very close to the interaction region, so we have to deal with the large radius or diameter of the beam pipe. Also here, so it's sort of for the students probably a really nice plot showing the impact of the vertex detector and the PID. So if you do not have your vertex detector or PID and you try to reconstruct, for example, this D0 mass, which is sort of combination of the proton and the kaons, this is what you will see. So as you can see, there is no even evidence where this D0 looks like. But if you just introduce like, the PID, that means you identify your kaons, this will be what you sort of, the peak started to emerge. But if you have at least 25 micron vertex detector, the nice and beautiful D0 signal will be emerging out of this background. Of course, you have, so we did the simulation because right now we don't have a detector. We do not know how it will behave. We have to really look at the performance with the GANT. So we use the GANFIT and RAFE at that point. And we try to see if this detector actually can give us, because as you can see, the parameters which we use, for example, for the smearing, really depends on how well you reconstruct your momenta. And we really need to know, where we are in this scale for the momentum reconstruction. So coming back to the current activity, and this is exactly what the user group are currently doing. So this they define the central detector, the bunch of criteria which goes for the colorimeter, to the PID, for the large acceptance, for the neutron tagging, and so on. I will not cover this yet, but I wanted to show you what are the really relevant for our studies. That we will have pretty good momentum resolutions, even though that we are right now discussing different options like all silicon or silicon plus TPC. So they are more or less lies next to each other. There is slight deviation depending on rapidity or what kind of magnetic field you're going to use. But so we are really comfortable that the tracking performance will be really good. So I mentioned that we have to keep an eye on the material budget, because for the this would actually make the life much easier if we for those slow pions. So I also probably skip this slide. Of course, if we introduce the support structure. So right now we are playing only with the sensitive elements and trying to get out of, momentum reconstruction out of the sensitive elements. But of course, the support structure will make the impact and will affect certain areas. But this is what we have to keep an eye on. Again, we made the estimation for the vertex resolution. So with this design, with the current technology, we are comfortable that we can get to the 25 microns vertex resolution. So this is a good sign, and like finger crossed that we can really build this. Also talking about PID. So if you just plot a mean bias, pions and kaons, as you can see, this will be the distribution in terms of the total momentum and pseudo rapidity. I will show you the link to the different technology in the electron and gap. We are planning to have modular reach, which will provide the pi k separation up to 10 GeV. So this is exactly the area which we are right now needed. So in barrel, it will be slightly complicated because this is the area where we need to place something radially compact. So Dirk will be one of the candidates, but it will have only limited capability, so up to 6 GeV. This is what we currently can achieve in this area. And for the hadron and cup, so we will try to have the dual radiator reach, and we can cover the momentums up to the 52 GeV for the pi k. So as I mentioned, in our LDRD project, we looked at the different channels. So this is how the spectra will look like for the D star, for D0, D star, D plus, D sub S, and even lambda C. So looks reasonable and very nice. But the overall efficiency is around 5 to 6%. And this is not really enough to probe your gluon or make some impact on the gluon density. So what we started to look at the inclusive models of the charge reconstruction. What we did, we just look at the kaons and made the projection to the kaon x of this displaced vertex. Yeah. So this is the displaced vertex or projection of the secondary vertex on the direction of momentum for the kaons. For the blue curve here shows all the mean bias kaons, and as you can see, most of them are peaking close to the primary vertex. And of course, we will have a lot of kaons from light quarks and also from the charm. So this is where they are sort of tend to go. And at Hera, we developed techniques how to actually the subtract of light quark contributions. And this was sort of made out of the fact that we can subtract this negative sign displaced vertex from this distribution. And this is what we actually, so the result of this subtraction leads to this plot. As you can see, it's, very well aligned with the charm signal. So out of those contributions, we estimated also the efficiency. So you can see efficiency in the bins of the log x and the log q square. You can see we can get from 25 to 30%, and it's quite uniform. So this is really quite uniform across the q square, x and the q square bins. Compared to the exclusive reaction. Yes, we can prove that this was exactly the D star or D0, but with the invariant mass, but unfortunately this, the efficiency is not enough. So we did look at the impact on the PDFs. So we used derivating. I will not have a time to show it today, but this is probably an extra talk. But as you can see here, there's a red band showing the impact of the EIC data And this is really, for large X region, this is really the large impact, in my opinion. So we are still improving our results. So we at the moment we assumed 10% of systematic uncertainties, but this needs to be evaluated more in the details, taking into account realistic response of the detector. But this, this is ongoing studies, and this I'm presenting actually a fresh new plot, which was actually made like 3 days ago. So let me switch to another operation. Do I have a few minutes? Very briefly.
Oh yeah, you're fine. You're fine.
Okay. Yeah. So F2 charm actually really interesting in the high X region on its own, because this is really unexplored area, and this is this plot show you a projection on F2 charm for the 10 inverse femtobarn, again taking into account reconstruction efficiency of 20%. So experience from here showed that the low Q square or low X physics, so the EAC, where actually the charm cross section is really dominating, are really important, and we are trying to actually get those measurements done for the EAC, but those measurements would require special instrumentation in a far backwards region. So we had a beam pipe monitor, a colorimeter installed next to the beam pipe, and this allow us to actually test this low X on low Q square region. So we are trying to get similar done for the EIC. For the beauty reconstruction, so lessons learned again from here are that we have really high suppression in terms of the cross section, like 2 orders of magnitude compared to the charm. And this cross section is mainly dominated by the photo production. That's why, the instrumentation of this low Q square area is really important. And we have really a steeply falling PT spectrum, so we need to pay attention to this. And the way how we reconstructed was that we had the charm jets, and we had a lepton, so in this case was a muon, and we just look at the PT relevant to the jet, and this was used for the beauty reconstruction. But I told about muon, but this has similar ratio to the electrons. That's why we have to pay attention to the lepton identification. So I will skip the slides. I just put it here because this is my baby project, lovely project which I am actually doing all my life. So on the transition radiation detectors, but this would allow us actually to help with the reconstruction of the leptons for the beauty and the charm decay, so that you can see the branching ratio are showing in here. So I also made some estimations on the beauty production with HVQDIS. As you can see here, compared to the HERA, so we had 1.6 nanobarn at HERA, and so similar reaction will be, the orders of magnitude lower for the EIC. But still, with high luminosity, this is what we can also study. So different methods, again, the semi-leptonic channels where we have from charm. So this we didn't touch in our LDRD, but probably will be nice topic to investigation at the EIC, where the both CEC bar pairs decay semi-leptonically, and you just measure actually the those either muons or electrons out of this together with some kerns. And also double tagging. So that means, so what I just told you before, we were not able to, we were able to reconstruct only single charm out of this pair, but in principle, you can look also to the events with double charm tagging, where one you sort of reconstruct inclusively and one exclusively, looking at the invariant mass spectra of the product. For those of you who really like beyond the standard model, I think this is the also topics which we could touch at the EIC. So with the leptoquarks, and again, so this was my PhD topic. So you can enhance the different branching ratio in the B. So this is a currently topic for the LHC and also Bell. But we could also try to look at those processes at the EIC as well. Charm and the diffractive process is really unique, and we had the first glance at the HERA, but as you can see, we didn't have the statistics in these areas, and the instrumentation for the far forward area for timing was not really done properly. So because it was introduced as sort of on the second stage after already building HERA Collider, now we can, with improved tagging, we can actually, also improve those data, as well as looking at the nuclear diffractive gluon density. So this will be really first time measurements at the EIC. Looking at the charm in the diffractive, so in the charge current reactions, so charm diffractive charge current reactions are really, third level of complexity. And this will be sort of complementary to the ongoing activities with neutrino facilities. But still, it looks like we have a really good chance for measuring this. So talking about charge current, again, this will be the topic for the probably next, lot of you are, and Steven's team and Fred are involved in these activities. Charm tagging in the charge current reaction would allow to probe strangeness contents of the proton, and actually the ability to have electron and the positron beams would allow to look at the ratio of the strange and anti-strange and really extract the PDFs out of this. So this is, again, I will not touch this. This will be the topic for probably next seminar on its own. And I just want to mention here that tagging the charge current is really tricky, because you will have a neutrino in the final state, and so it's not it's really difficult compared to the neutral current reaction. So that means this charm jet will actually serve also for the kinematic reconstructions with the Jacques-Blondel method. And we have to really pay attention to the next generation of the detectors in order to improve the resolution. So this brings me to the topic on the jet identification. So again, I will not really talk about this, but I just would like to mention that for the jet, especially for the heavy quark jets, it's really important to have the high granularity calorimeter to study subjet structure, and to be able to identify a heavy quark jet from the light quark or from the gluon or from tau jets. And here is where the machine learning algorithms could really play the role, and maybe also as a next step, actually bring them to the online analysis. So this is my dream, but I hope this will be the reality for the EIC. And the last topic, before my summary, is of course, once we have we know and understand and control actually the heavy quarks, we can also look at and compare this and look at the emerging properties of the hadrons, like how this where those jets are emerging, how they are propagating in a cold nuclear environment, if there is any PT broadening, because depending on the path inside the ion, or we could have some impact. And this is the ongoing studies also to see the PT losses of the heavy quarks or light quarks, depending on the PT. So this brings me to the summary. so charm is really exciting topics at the EIC. So we have a lot of opportunities. So next generation of the detectors would really help us to actually improve the efficiency. And I hope I convince you that we can do these topics with at least neutral current reactions. And there are many other applications, like in the photo production, in the diffractive channels, in the charge current, and even in the beyond the standard model. So thank you very much, and I'm open for the questions. So actually, yes, I found a really nice definition of the particle scientist: ability of quarks and gluons to think about quarks and gluons. So I really like this. I hope
the old adage of the old adage of the universe pondering itself, right? That's what human beings are. Yeah. Yeah, no, thank you very much, Yulia. And we like to throw in just a little bit of maybe like canned applause here at the end as best we can, because we can actually get real applause for you. So thank you very much. There are questions from Pavel. So let me get Pavel unmuted here. You should be able to unmute now, Pavel.
Great. Thank you for allowing me to unmute myself, Steve. Hi, Yulia. Well, thank you. It's very amazing to see the progress that you have made in studying the physics prospects at the EIC since, well, last time we talked about it in sometime in February. Yeah, thank you very much for this presentation. I have two questions. So the first question about the chart of the coverage in the X and Q squared that you were showing for measurements like deep-inelastic, well, let's see, inclusive deep-inelastic scattering. So I was wondering if it is possible, in addition, not just about for charm, but in general. One question that we discussed is whether we could look at inclusive data structure functions in a more detailed way. For example, if it could be possible to classify events according to the final state multiplicity. So let's say we measure the structure functions, but in addition, we separate events with large and small hadronic multiplicity. Is it possible to do it at the EIC, or this is something that, well, will be difficult?
I think yes. So first of all, so if you compare this with the HERA, we will have at EIC, we will have the different methods how to actually reckon. So we will have a possibility to measure jets. That means you actually can extract those with one jet, with the two jets, and so on. But also we have really good instrumentation for the single hadron measurements. That means we can really group those events on those which have one hadron, two hadrons, and multiple hadrons. So that means we really will have ability and identify them, because we will have a PID. This is what the HERA actually didn't have. And this would allow us to improve also upon the kinematic. As you can see here, for example, for the Jack-Blondel method, this is like the sum looping over the different hadrons in the final state, and similar here. And this is what we will use actually to improve the kinematic coverage. So if we just look at not only the scattered electrons, but also we'll take the hadrons in a place, this would allow us to measure and extend actually the resolution for our kinematics beyond just little band over here. Similarly at EIC, so if you just look at this kinematic plot, so as I mentioned, the most of the data, for example, this electron method would allow also to only measure this little band over here. But we will have ability to run with the different energies. That means we can shift this band all across the XQ square plane, because we will touch the different center of mass energy settings.
I think this is great, especially well the fact that you can measure the individual hadrons and count them. Yes. Well, this will be a very interesting measurement, for example, at large X, to see if you see differences in the structure functions depending on the multiplicity of the final state hadrons.
Yeah.
Now, I have the second question about the charm reduction, and well, of course, you showed this well-known diagram for the boson-gluon fusion, right? And then we say that we use it to measure the parton distribution in a very complex object like a heavy nucleus. But I was wondering, well, in principle, this diagram has substantial corrections, and not just from the high order radiation, but also higher twists. And so also the, well, I think we could imagine, as you mentioned, that there will be some interaction between the initial and final state that will modify these measurements. How are you going to deal with it? How will you distinguish between these various scenarios?
So this is a really good question. So I don't know if I have an answer to this. But I think so. We first have to really understand how it goes with a proton, right? So we have to understand all these properties of those heavy flavors when we just looking at the single proton. And then, you know, we have to increase the level of complexity and see how this will change the behavior of those, you know, jets or properties which we are trying to look. And this is, you know, really, I think, complex questions. Yeah, I'm correct. You know, you're correct that, you know, this would allow a lot of, you know, theoretical support on this, how to understand some different radiations effects and initial state radiations and so on. And also what I mentioned in my last slide, this propagation through this, the nuclear matter. So this is really, where I can. So this is really, you know, unique, and this is what I think we would have to answer within this 10 years of the AC program. How they actually, you know, what will be the effect on the different hadron properties, on the PT, on the broadening, or where the actually hadrons are emerging, right? So not only how they are propagated along this, you know, the heavy nucleus, but are they really involved in from the quark to the hadrons inside the vacuum, or inside this dense called QCD soup of gluons, right? Yeah.
Yeah, well, this is all very interesting, and I think this is a fascinating opportunity to study these effects. So thank you so much.
Yeah, that's okay.
Yeah, thank you,
We just started. I am not really claiming that I think this is just the beginning of all the studies. So we just touched little corner, and I think, you know, within the next year, before the construction, before the first collision, we have to try to get, you know, up to the speed and try to answer all the other questions. Right?
Yeah, I think it's very good you formulate parameters for these measurements, because then we could run all the simulations that are necessary to better understand this, well, the differences between the scenarios.
Yeah. So what I can offer you guys, so I have the running tools from HERA. So we have the running tools for this HVQ DIS. They are running, so we can compare the charm ratio and you know, the beauty, and for the different, you know, the Q-square ranges. So we have it enhanced, and unfortunately, I do not have anything what really, I don't know how to modify these HVQ tools. Maybe we can discuss this offline for the heavy ion environments, right? So it's only designed for the protons, but we need to put some corrections for the ion operation. And I think it will be a, you know, very powerful tool. As you can see, it shows, you know, a very good agreement, at least for the proton case. But you know, this will be really good tools for the EIC to use.
Yeah, it was a great tool during the HERA era, and I'm glad we are looking at this again, because clearly we can learn a lot about QCD from these measurements.
Yeah.
All right, Tim, you had a question.
Yeah, I did. So first of all, Yulia, thanks for the excellent talk. So I had two questions. One is a technical and quick one following this discussion, and then a broader question. So the first is, Do you have a sense, you and your experimental colleagues, really just how systematic uncertainties, or really any uncertainties, differ in the nuclear scattering case, heavy quark production from nuclei, as you're talking about, compared to production off the proton? And then I can ask my second question and just I'll shut up. The second question is, you mentioned BSM opportunities or BSM searches involving heavy quarks. I was wondering, it might be a general interest to this audience if you elaborate on what you have in mind. Just give me a minute or so. Thanks, Yulia.
So answering the systematic uncertainties, so this is not what we really looked at, during our LDRD studies. So we just used the numbers which we used at HERA, which is roughly 10%. We started to look at the combined information because at that time, so that this LDRD project runs like a couple of years ago. At that time, we didn't have this powerful machine of the user group community who really put together all the detectors. So I think right now is the right time because we already have a concept of the sort of reference detector, and we could start looking at the uncertainties. So the main, so if I remember correctly, main uncertainties were coming from the momentum reconstruction and vertexing and luminosity measurements. But but there was a list of like 10 to 20 different parameters, and I'm just picking one which had really a major contribution. And I think we need to really, within this user group activity, we really have to look at this more carefully and estimate this. For the BSM searches, I just listed what I found, in the literature, and so I think just looking at the different the branching scenarios. Decay scenarios of the beauty quark or some charm D0, for example, decaying to the mu plus mu minus pairs, or D0 decaying to E plus mu minus. You see the different charge, different species. So I think here what is really important is to provide, first of all, good instrumentation, for example, for the muons or for the electrons, so that we can really identify them properly. And and secondary, we have to, in addition to, so my opinion that, as I told, like this nice BGF process provide you sort of the pair of the CC bar. So what we can look at the one charm decaying to the sort of into the standard model way, and another one decaying sort of in a BSM part of the model. So this is what we can probably compare. Also, we can compare the different ratios, looking at the ratio like CC bar or BB bar, and see if we will have some enhancement or something like this in different branching scenarios. I didn't look at this more carefully, but this is probably for the newcomers will be really good opportunities to look.
Excellent. Excellent. Yeah, thanks, Yulia.
I'm sort of riffing off that theme a little bit. I haven't heard anybody talk about rare, like dark gauge sector searches that could be done at the EIC. Are you aware of anybody that's talking about, say, dark boson searches using this kind of high intensity EA collider?
We have a group looking at this BSM topics. Even actually, we put some sort of snow mass proposal for the BSM search at the EIC, where we indicated multiple channels. For example, this charge-lepton flavor violation, where you, let me just go to the standard, the DAS diagram, where you have leptoquarks or some SUSY particles involved. And oh, yeah, for example, let me go to the DAS. Yeah, for example, this one. So you have instead of gamma or Z, you have leptoquarks exchange, and you have sort of not the electron, but the muon or tau in the final state. And this would give you a sort of ability to probe this charged lepton flavor violation. So we also looked at the charge current reactions where with a different polarization of the initial lepton, you can probe a right-handed W, for example. We also looked at the heavy photon search. So the heavy photons, this is what, and this would allow us actually really expand the area of the masses of those, those heavy photons. So we have a group working on this project as well. And so we recently had actually a bunch of the workshops related to for example, operation with the positron beam. And the multiple, sources indicate that this is what we really need. In May, we had also a small scale, like few days workshop related to the electroweak and BSM physics. This is not really just for clarification, electroweak and BSM is not really in the mainstream of the EIC physics program. So this is really a good addition. But I think this is a really good addition. So we can really make a lot out of this. And taking into account this high luminosity, and if we will have like next generation of the detectors, we can improve multiple things. So what we also looked at the like Lorentz invariants, how to probe the Lorentz invariant. So we had a lot of ideas. So it's really, sometimes even crazy ideas. But yeah, I think this will be really good topics for the next workshops to discuss, right?
And if you don't mind me asking one last question, because I don't see any more questions in the speaker queue. So I think maybe one note to end on would be the following. This is, as you said, this is a very interesting time to get involved in the EIC because you can still influence the future at this point. How can students get involved in the EIC when, there's no obvious source of federal funding for it yet on its own, but students nonetheless might be enthusiastic about spending time at a lab like Jefferson Lab? Are there opportunities to bring students there and partner them with other people to work on projects that are important right now?
Absolutely. So just one of the examples, we still have, even so that JLab, was not selected as a sort of host for the EIC, we still have the EIC Center. And thanks you for reminding me this. So we have, every year we have, a list of the proposals or some funds available for the students or postdocs to join. And actually it's organized that they're sharing the time 50-50 between the universities and the JLab. And so they pick up the lovely topics, or they look at the list of the suggested, the topiks for the EIC. And I think this will be, really good opportunity for them, for example, partnering with the JLab. But just talking in general, I think right now the EIC era is just started. It started with the site selection, and we need to grow, because without our students, so this accelerator is for the next generation, and we really have to engage them at the early stage so that they are really experienced in the time when this accelerator really will be built. And I think starting with the physics analysis and diving into this simulation of the different subdetectors, or looking at the systematic uncertainties, once the detector concept will more or less settled, actually. So the next year, as far as I heard, there will be call for the detector proposal. That means, by that time we already will know which groups will build what kind of subcomponents and how the EIC detector will look like. And I think this is really a good time within this year really works towards this approach. Again, at the JLab, we have a lot of opportunities for the beam testing. So if there is some hardware in mind on the testing different detectors, so we can help to organize this test beam opportunities. But I think the heavy flavors, what I try to show you right now, so this is like open-end subject, so you can really look at from the different perspective. I mentioned at the end of the slide, like this forward or diffractive processes with the charm. So this is really brand new topic. So this is where we need our students to help and to work. So if we, for example, understand more or less how BGF process works, but this diffractive part is really brand new and would really actually require some work together with our theory groups and Monte Carlo community to actually build Monte Carlo samples which are necessary for our simulation. So I think this is really just the beginning.
Yeah, no, it certainly seems like it, and you did a fantastic job of communicating all this. So I think with that can't end on a better note than optimism about the future, I think. So thank you very much, Yulia, for this fabulous seminar. And with that, I think we'll close out for the evening. And I wish everybody a healthy evening and a safe week. Okay. All right.
Thank you.
Take care. Thank you, Yulia.
Bye.